Okay, today we talked about limits of a function yesterday. We're going to go further into this today. And we're going to look at the algebraic part. So let's look at this function x squared minus x plus 2. If I do a table of values and I start to get closer and closer to 2, so I enter values of x that are getting closer and closer to 2 of x, you'll see that my values start to get closer and closer to 4. So that basically means I am approaching 2 from the positive side. Okay? Or sorry, approaching 2 from the negative side, I should say. So we're approaching 2 from the negative side. We can see that our value is getting closer and closer to 4. Now, if I look at it this way, and this is approaching 2 from the positive side, that's what that notation means. We can see that our values here, we start at 8, and we start to get closer and closer to 2, or to 4, I should say, using our values of x, getting closer and closer to 2 from the positive side. So we can see that as this function approaches x is equal to 2, or we'll do this again, redo that. This function approaches 4 as the x value approaches 2. Now, with this notation here, because I seem to have messed up, I don't know if it's the same if I fixed it on yours. So the limit as x squared minus x plus 2, so the limit of this function as x approaches 2 is equal to 4. So what is happening to the function as we're getting closer and closer to 2? It is not necessarily what the value of that function is, but what happens as it approaches. Now, in this case, yeah, the value of that function is 4 when you plug in 2. But that's not the case for all of them. Okay? It is in this case, but not for all of them. Okay? So we write this as the limit as x approaches a some certain value of f of x is equal to the limit. So the limit of f of x as x approaches a is equal to L. And that's what this notation means here.
Roland Dolan, could you please come to the office?
So this function here, I read this, the limit of x cubed minus 2x plus 8 as x approaches 3. What is it? Okay. Now, in this case, we're going to look at this in terms of what's happening. We're going to use some properties of limits to help us. Okay. Now, in this case, what happens if I plug in 3 to my function? 27 minus 9 plus 8, so 27 plus 1. This works out to be 28. Now, that is said, it's not always that case. In this case, it is. The limit of this function as it approaches 3 is equal to the value of this function at 3. Not always is that the case, and we sometimes have to use a little bit of work to get there. So let's take a look at the properties of limits. So we have two limits. Limit of x approaches a of f of x, and the limit of x as x approaches a of the function g of x. So if you have the limit of the sum of two functions, this can be written as the limit of one function plus the limit of the second function. Oops, I want that, I want b of x. Same thing with this one here. The difference is the difference of them. I'm going to be a little lazy and not write it out. So the difference of the limit of the difference of two functions can be written as the difference of two limits. That sounds strange. Now you've got the limit of a constant term times a function. This is going to be the constant term times the limit as x approaches a of that function. Now we can we can show some work with that later on, but essentially when we get down to here, we can do that. We can prove that later on. Okay. So here we have the limit of a product of two functions. We can write this as the limit of one function times the limit of the second function. A similar proof could be made for this, the limit of one function divided by the limit of the denominator. Okay, so basically we get to do all of that. Now here, we're taking a function, raising it to some power, and then taking the limit. Well, we can do the same thing here, and there is another property. Again, we're not going to prove it. We have the limit as x approaches a of f of x. And then once you take that limit, you can raise it to the power of n, assuming n is a positive integer. And finally, with a similar idea, because here we have a rational, the square root, so this would also apply to cube roots, etc. This can be written as the square root of the limit as x approaches a of f of x. So again, I'm not going to ask us to prove this, but we just have to make sure that this limit here, the square root of can't be a square root of a negative number in this case. So assuming that this square root exists, and this bottom one or top one if it's an integer. Now, there's a lot of different reasons or ways we can use this.
Colin Hamilton, could you please stop by the office?
We're going to, starting with the limit properties up here and these limit properties down here, we're able to compute a lot of different limits. The limit as x approaches a of x is a. That's okay. So the limit as x approaches 2 of x is 2. We're just going to substitute in whatever here. The limit as x approaches a of x to the n is a to the n. So we get to replace that entire thing with a to the n. Limit of as x approaches a of a constant is that constant. And then the limit as x approaches a of the nth root of x is equal to the nth root of a, assuming that it exists. We can't have the square root of -2. So we wouldn't have that x approaches -2 of this. It wouldn't work if that was n was a square. So now I don't usually do this, but I'm going to break this apart and to treat it with our limit properties. So we've got the limit of a function plus a function plus a function. So limit as x approaches 2 of x squared plus the limit as x approaches 2 of 5x plus the limit as x approaches 2.
Mr. Holby, you have a phone call on 1500.
And so now we can evaluate these limits using what we have up here. Okay, so this limit as x approaches 2 of x squared will be 2 squared. The limit of this would be 5 times 2. And then the limit of this would be 4. So we have 18 is our answer. And that's, so you can, and we're going to do this in the next couple of ones, and then that's about the last time we'll do this, because it will start to be intuitive to us later on. Something like this. The limit as x approaches -2 of this function. Well, we have our properties of limits, so we have x cubed, limit of x cubed plus 2x squared minus 1. So x approaches -2 over limit as x approaches -2 5 minus 3x. And to be a little bit more complete than we necessarily will be later on, we will apply the limit properties to everything. X cubed plus the limit of 2x squared plus the limit of -1 all over limit.
Mr. Hovey, you have a phone call at 1500.
Just give me half a second. Sorry, and then we'll evaluate. So -2 cubed is -8. Here we have 4 times 2 is 8. And we have the limit of a constant is plus -1. Limit of a constant is 5 minus, so here we would have -6. So -8 plus 8 minus 1, so we have -1 over 11. And that's our answer here, -1/11. Assuming I haven't lost a sign somewhere, because I'd be known to do that. Okay. So that's, again, using our limit properties. We can intuit that a little bit more later on. Here, I'm going to treat this as the limit as x approaches 3, 2x plus x squared. I'm going to take the square root of that when I'm done. That's
Mr. Hovey, you have a call on 1500. Mr. Hovey?
I'll follow that. That's, I don't know, 20 minutes. All right, distracting me again. So here's our limit properties. We take this, we want to do the limit. Well, let's take the limit of what's underneath the square root sign and then take the square root of that. So again, now we've got the square root, the limit as x approaches 3 of 2x plus the limit as x approaches 3 of x squared. So again, we're applying our limit properties. We don't do this all the time. So now we have the square root of this becomes 6, and the square plus the square root of this becomes 9. So our answer is the square root of 15. Now, like I said, we could probably do that just by plugging that in there. But this idea of using the limit properties to help you with this, to get an understanding of this now and then go forward with this, that's why we're doing it this way. Okay. Now, here we have a graphical version. We have the limit of f of x plus g of x. Well, I don't really want to draw the graph of f of x plus g of x. So I'm going to say, okay, as a limit as x approaches 0 of f of x plus the limit as x approaches 0 of g of x. Now let's see what happens. What happens as f of x approaches 0? It gets both sides, it's equal to 3. And the limit as g of x approaches 0 is -1. So this is equal to 2. Now, these have limits at that point. There's a few places they don't have limits. There's no limit here, There's no limit out here and there's no limit there. And we'll talk about that, why that is in a second. Okay? So here we have the limit as x approaches -3 of h of x times f of x. Limit x approaches -3 of h of x times the limit as x approaches -3 of f of x. Well, let's look at h of x. As I get closer to -3, okay, here's our -3 out there. I have what is called a right-hand limit. As I approach it from the positive side, it gets closer to 0. But it doesn't exist out here. Okay, there's no limit out here. There's no left-hand limit. So this is undefined. And we can see the same thing with f of x. There is definitely no limit out here as it approaches -3 because it doesn't approach -3. It stops at -2. So what we have here is a board that's driving me nuts. What we have here is this limit is undefined. There is no limit because f of x doesn't approach -3 and h of x approaches it from the positive side, but not necessarily from the negative side. So there is no limit for that one. So here we have the limit as x approaches 0 of f of x over h of x. We'll take the limit as x approaches 0 of f of x and divide it by the limit as x approaches 0 of h of x. So again, as f of x approaches 0, we have our -3. Or sorry, not -3, +3. Our y value is 3 at that point. As h of x approaches 0, it's down here at -3. It's got a left-hand limit, it's got a right-hand limit. So we have 3 over -3, -1. With this one here, same principle. I will evaluate the limit as x approaches 1 of f of x. Limit as x approaches 1 of g of x. So f of x as it approaches 1, we can see that approximately approaching 2. We have a left-hand limit, we have a right-hand limit, so I'll substitute in 2 for that limit. And then as this guy approaches here, as approaches 1, g of x is approaching 0. So 2 over 0, that's not good, that's undefined. Because we cannot divide 2 by 0 to get an answer. This one, I'm going to take that constant, I'm going to move it outside. Limit as x approaches 1 of g of x. We just did that one, that's equal to 0. 3 times 0 is 0. Okay, so here we have, I just introduced the concept of left and right hand limits, which we'll go on to on Monday, or on the next class. And the idea of you do not have a limit if you don't have both a left-hand side and a right-hand side, and you don't have a limit if it doesn't get to the value that you want to approach it at, or where you want to evaluate it at. If we were to use basic limit properties here, we would run into a bit of a problem with all of these. This is that where I mentioned we have to sometimes trick the math to work. So if I just use basic properties, limit as x approaches 2 of that over x minus 2, top, using our basic properties. Don't really care what's on the top, but here we have 0 over 0. Again, I talked about this a couple days ago. 0 over 0 is not defined. Similar with this one. Limit as x approaches 1 of this over limit as x approaches 1 of that. We end up with 0 over 0 again when we evaluate it. Here we're throwing in an h. It doesn't matter. It's just another variable. The limit as h approaches 0. Get that on the bottom. So we plug in 0 here, we get square root of 9 minus 3. So again, that indeterminate form 0 over 0. We don't really know. Here we have similar limit as h approaches 0. 2 plus h squared minus 4 over limit h approaches 0 of h. So here we end up with 4 minus 4. So again, we have that indeterminate form. So when you try to evaluate your limits using the basic properties of limits, and you end up with one of the indeterminate forms, you've got to do some algebra to see if you actually can get something that isn't indeterminate. Okay, so I can't have 0 over 0. Well, let's do some algebra first with all of these guys and see if we can maybe simplify it a little bit and then take the limit. Well, limit x approaches 2. This factors out to x minus 2, x plus 3. So now we're taking the limit as x approaches 2 of x plus 3, which is 5. Now remember what I said before, all of those ones that we did over here, we could just essentially plug in -2 and get an answer out, because the limit is equal to where the evaluation, when we evaluate at -2. We're not able to evaluate at +2 for this guy, so we have to do a little bit of work. The limit is 5. What we're going to see, if we were to graph this equation, you would have a graph that looks like this with a 0 at, or not a 0, a dot at 2, a non-permissible value, hence what we have here. Similar here, okay? We know it's indeterminate if we just evaluate it, but let's factor the top into its conjugates. We know those cross off. So the limit as x approaches 1 of x plus 1 is 2. So if you were looking at this function, okay, again, you would see a hole at 1 and a y value of 2, but the limit is 2 because I'm getting close. I have a left-hand limit. I'm getting closer to 2 as I approach 1 from the left. I have getting closer to 2 as I approach 1 from the right, and we have a limit, even though that function does not exist at that point. Now, both of these functions here are a little bit different in that maybe we have to do something else. Now, something like this, you've got it squared or cubed. Let's see what happens when I manipulate this function by squaring. Limit as h approaches 0, 4 plus 2h plus h squared minus 4 over h. Now you can see here the 4's cancel each other off. And we have a common factor of h. Now, by manipulating that, hey, those h's are going to go away, which leaves us a limit as h approaches 0 of 2 plus h. and you plug in your 0 for h, and your answer is 2. This is why we did a fair bit yesterday on the, 2 days ago on rationalizing the denominator, or numerator. Okay, I can't do the same thing. I got a square root. Crap. Well, let's get rid of the square root in the numerator and see what happens. So I'm going to multiply this by the square root of h squared plus 9 minus 3, or plus 3, over the square root of h squared plus 9 plus 3. So since I'm multiplying by the conjugate, this middle terms disappear, so I end up with h squared plus 9 minus 9 over h squared plus 9 square root plus 3. Our 9's disappear, so we have the limit of h approaching 0 of h over this. Now we can go ahead and plug in our zeros, so we end up with 0 on the top, the square root of 9 plus 3, 0 on the top says I have a 0 on the bottom. So that's one way, or another way of rationalizing the denominator. That's where rationalizing the denominator comes in this case. So in this situation, the limit as h approaches 0 is 0. Just want to find one more thing. If it's here. Okay, so let's do one more that's not on the. Oh, there it is. It is on there. I forgot it was there. What the heck is this? Well, I cannot plug in 2 because I'm going to get 0 here. Now, that thing up top bothers me. Let's see if I can simplify that top and see what happens. So I still have the limit as x approaches 2. I have the top, so I need a common denominator. So 2 over 2x. That would be x over 2x. So I've got 2 minus x over 2x divided by x minus 2. Okay, just to tidy that up by flipping and multiplying the denominator. Now I cannot cross off 2 minus x and x minus 2 until I take a common factor of -1 out. And now I'm able to cross this off. Now I've simplified that down to the x's limit as x approaches 2 of -1 over 2x. We are now able to plug our 2 in, or evaluate at 2, so we have -1/4. Okay, so not relatively simple. You have to recognize what you're doing. So first, I try to, if I have an indeterminate form, I try to factor as I did in both these cases. If I have a power, whether it's raised to the power of 2, possibly raised to the power of 3, and if I'm really nasty, raised to the power of 4, I would expand that. And we're going to talk about how to use the Pascal's triangle to expand that really easily. That one's easy because it's just squared, but cubed is also fairly easy. If I end up a radical in the numerator, apply rationalizing the numerator. And in this case here, right, what I do here is because I don't like the way this looks. I've got a rational expression up top over a number, a fraction divided, or a fraction within a fraction. So I'm going to try to get rid of that. I'll spend a little bit of time on Monday making sure that you understand this. This is your homework for the day. The answers are in the back of the textbooks. If you have questions, please text me or whatever. I'll be sitting on a basketball court all weekend, so I shouldn't have a big problem of answering. Thank you. Have a good day.